Okay, so welcome back. Now what we're going to do is we're going to do an example, and we're going to show how to use the lemma, the previous lemma, to show that S here is a subspace. Now, the lemma says, okay, obviously this is a plane through the origin, so it's a subset of R3, right? So we're going to use the inherited operations of addition and scalar multiplication inherited from R3. Now, the way we are going to typically prove is instead of, because all of those three statements, 1, 2, and 3 are equivalent, we're really going to focus on 2. Because really all we have to do is show that S is non-empty, right? It has to be a non-empty subset of a subspace, of a vector space, rather. And then show that it's closed under linear combinations of any pair of vectors in S. If we do those two things, we're done. Everything else is done. So, it's easy to show that this is non-empty because the zero vector is in here, right? Because if you put 0, 0, 0, right, if you have a zero vector in here, you get 0. Okay, so the zero vector is in there. And then all you have to do is show that any pair of vectors in S, right, is added is in S, right? So if you take a linear combination, so if you take R1, S1 plus R2, S2, right, where R1 and R2 are real numbers and S1 and S2 are elements of S. So we'll do this. So we have R1 times X1, Y1, Z1 plus R2 times X2, Y2, Z2, right? And so if we do this, we're gonna, what do we get? We get R1 R1 X1 plus R2 X2, and then we get R1 Y1 plus R2 X2, and get R1 Z1 plus R2 Z2. Ooh, R2 Z2. Anyway. So now here's our vector, right? So now how do we show? We want to show that this satisfies this, right? Because if it does, then we know it's in S. Well, we take this, let's take R1 X1 plus R2 X2 minus 2 times R1 Y1 plus R2 Y2 plus R1 Z1 plus R2 Z2. So now all we have to do is do what? Use our normal adding, your normal properties from R3, right, for that we know, and we can rearrange these, right? So what we can do is we can rearrange these as this. We'll get yeah, so if we rearrange these, we're going to get R1 times the quantity X1 minus 2 Y1 plus Z1 plus R2 times x2 minus 2y2 plus z2. Let me see here. Yeah. Yeah, because we get R1 minus 2 R1Y1 plus Z1, right? That's good. And then we get R2 minus that. Yeah. So guess what? Yeah, now watch what's this, right? Right? This is an S, so this turns to 0. This is also an S, that turns to 0, and so it all goes to 0. So we're good. And that's it. So we would be done, right? But there's another way that we could show this. Okay, so that would be the way we normally would show that S is a subspace of R3. Now, here's another way. We could think of x minus 2y plus z equal to 0 as a one equation linear system of parameterize it by expressing the leading variables in terms of the free variables. So we could say, okay, let's take this and we can rewrite it as, let's write x equal to 2y minus z, right? So y and z, it's a system of equations with only one equation and three unknowns. So these would be your free variables. This is your leading variable. So we're going to rewrite this, and then we're just going to have x equal this. So our vector, right? Our vector would just be zy minus, not zy, 2y. 2y minus z, and then we have y, and then we have z. And so that would be the way we would write the vector. And so we could write S like this. Right? But we could also write it like this. Let's split this up. So this would be let's see. Right? such that, again, Y and Z are real. Okay, so now that we have it like this, to show that this is a subspace, we're going to consider a linear combination of R1, S1, R2, S2. Okay, so let's consider oops. Now, each S sub I is a linear combination of the two vectors up here. Right? So each S sub I is a linear combination of these two vectors. Okay? So what we rarely have, if you think about it, is a linear combination of linear combinations. And so what we're going to end up using is the linear combination lemma that we talked about earlier. So let's do this. Let's rewrite this. And so our equation is going to look like this. That's a 2, not a Z. Okay, so here's S1, right? R1, S1 plus R2. And then here's our S2. Right? Now, the linear combination lemma shows that the total is a linear combination of the two vectors. And so, the lemma's statement in number 2 is satisfied, right? Because we have a linear combination of two vectors. And that's all we needed to show. And so therefore, we're done. So that's another way of using. All right. Have a great day.